introduce the team real quick, say a few words to what software we use, and then have a look at our monocoque simulation workflow. I guess there's a really big number of new people to Formula Student here, so we decided to go more about the basics and not so much into the details. It just will come later today, I think. Yeah, to the history of car racing, the club was founded in 2006 with a combustion car. In 2009, we built our first monocoque concept. And we manufactured it with wet laminate and infiltration. In 2010, we also started in the electric competition. And in 2017, we had our first driverless car. And in 2019, we first used carbon fiber prepregs to build our monocoque. To the team, we are about 70 people. At the moment, we only build 2 cars anymore, no combustion car anymore, because we have too few people. So if anybody studies at Karlsruhe, feel free to join. Here you can see our latest run-in cars. Due to Corona, we don't have any 2020 cars which run. In the front, you can see our driverless car. Really nice car. It runs pretty stable and smooth. Also was successful in Formula Student Germany and in Formula Student Spain with second and first places. In the back at the right, you can see our electric car. Few highlights are self-developed electrical engines, the monocoque, of course, and the heat roll suspension setup. And at the back left, you can see our combustion car, which sadly we will not produce anymore. Yeah, general, when we start with a new car, we gather a few people and gather a few old parts and some cardboard. And then we set up a basic idea of how we want to package everything. Then we go into CAD and we model everything and do some calculations if everything fits and kinematics work and everything. See where the collisions are, stuff like that. And after that, we start with the simulation part. For simulation, we use 3 main programs with respect to carbon fiber. We use the multi-scale designer from Altair. It's a really nice program where you can really find out the details and the behaviors between your metric system and your fibers. Second software we use is EtherComp. It's a quick and easy tool to do fast simulations. We especially use it for our SES, which you have to do when you use a monocoque for your car. It's less complex than HyperWorks, and it gives you a quick understanding what happens if I add another layer of carbon fiber, or what happens if I change the direction in this layer, or something like that. You also have access to a large data bank, and you can just quickly find up a layout for your SES structures. And the main program we use to simulate details is HyperWorks. It has a huge variety of functions and it's really, really accurate. Why we do this? Well, obviously every Formula Student team wants to minimize the weight of the monocoque while still obtaining a reasonable stiffness in the monocoque and to get the manufacturing playbook. The stiffness you need because otherwise your suspension team will come to you and say, well, all the work we've done is worthless because you build a wobbly monocoque. And there's also this aspect of structural safety, for example, at your suspension mounts or your harness mounts. You want to be sure that they don't break. How we do it is by the standard approach for composite optimization in HyperWorks. The first step is free size, then you do size, and then you shuffle. We added an extra step. We optimized reinforcement, and after that we do a two-step validation on a torsional testing bench, and we also do an ultrasound check. Yes, as I said, there's basically 4 steps. First, you set up your model with all the forces and so on and so on. Then you do the free size optimization, then size, then shuffle, and the topology optimization. And in the end, you want to obtain a playbook. For the model setup, we use 3D volume elements for all the consoles. Like here you can see rocker mounts or the ski level bar. You model this in 3D. For all the carbon fiber parts, we use 2D shell elements in order to have a really nice look at the layers later on. For simple stuff like push rods, pull rods, wishbones, we use 1D tube cross section elements. And to connect all of these, we use 1D rigid elements. The forces we attach directly to our suspension. The forces we obtain basically from our left-hand simulation. You know how fast your car will accelerate, what's the mass, and so on and so on. And then you get the forces in the tire latch, and then you can use some technical mechanics to figure out which rod will obtain which load, and then you can model it in HyperWorks. As I said, next up is obtaining really precise data about your carbon fiber you use. Of course, you should have a data sheet. In addition, we use multiscale designer and ethercomp, and of course we do physical testing to be sure that there's no mistake in any of the simulation or in the data sheet. Then what I want to emphasize on is when you do your model setup, make sure your fiber direction is correct. You work with carbon fiber. So if you deviate from the direction by more than 10 degrees, you only have 10% of the E modulus left. And if you don't say HyperWorks how the orientation is, or later on when manufacturing, you think 0 degrees means something other than you set in your simulation, you will run into problems, and in the worst case, your monocoque breaks. Yes. Then first step, free size optimization. What's the goal? The goal is to reach an optimized material distribution for all the load cases you put in. So what you basically do is you set up your simulation, you put in your material data, and you put in a laminate. And what we do is we set up 4 main directions. It's 0 degrees, 90 degrees, 45 degrees, minus 45 degrees, and the core, obviously. We always go with a symmetric. We use a symmetric way layout. So after the core, it just is mirrored. And what we set as restriction is the maximum thickness you have. So you still can put your stuff into the monocoque, like batteries, drivers, engines, whatever. As a response, we set up the mass and the weight compliance. The mass is important because obviously you want to minimize it. And the weighted compliance we set up because this is how you optimize the stiffness. And what we do is we set as an objective to minimize the weighted compliance, so you optimize the stiffness while constraining the mass. So we set up a maximum mass, which is the target mass of our monocoque, which we get from our overall vehicle goals. We set a target weight for our car, and then you can distribute the mass across the sub-teams. And then we say we want a monocoque with 15 kilograms, so we set up a maximum of 15 kilograms for our monocoque and see what happens. If we find out the stiffness is too low, we have to increase the mass. If we find out, hey, the stiffness is really high, we try to reduce the mass even further. Yes. One little tip, when you run this with the standard setups of HyperWorks, you get 4 ply shapes out of every direction. You can change this to get 8 ply shapes out of every direction, and this basically allows HyperWorks to really refine the patches at certain areas. So you only have more layers but smaller patches, and then in the end you get more stiffness by less weight. Next up is the size optimization. Here you have to set up your manufacturing restraints, at least some of it. As you all know, one layer has a certain thickness and free size. The HyperWorks does not care about the thickness you can manufacture, so it will give you an optimized thickness, which is not manufacturable. So what we do is, for example, here you have a thickness of 3.14 millimeter. Let's say you can only manufacture, your layer thickness is 0.2 millimeters, so you can only manufacture 0 millimeters, 0.2 millimeters, 0.4 millimeters thicknesses when you stack the layers. And what we do is we set up a lower bound and an upper bound, and the upper bound is always a multiple of the layer thickness we have. And what you get is basically a sliced version of this. So here you have your 0 degree, your 90 degree layers, your 45 and minus 45 layers, and then it slices them, for example, into 2, 3, or 4 layers each. And then you get a manufacturable thicknesses. And what you also need to do is you need to address the shape of each element, because as you can see here, the shapes are really interesting and really optimized, but you can't manufacture it. So what you need to do is basically you need to do a little small squares or circles, so you can actually cut them and lay them, because you can't lay a patch that is 1 by 1 millimeter or something. Yes. After that, it's almost the final step. We do the shuffling. Shuffling basically means you will shuffle around the layers. So with this setup, you will not get optimal stiffness, and you will also run into problems with delamination, because if you stack too much fibers in the same direction, they will delaminate. Here we add some more manufacturing restrictions. For example, we set up a pairing of plus minus 45 degree layers. So if we have a plus 45 degree layer, we also want to have a minus 25 degree layer. For optical reasons, we set up a cover layer which we want to be 0-90-degree twill. As a response, we do not have the math anymore, because if you just shuffle around the layers, the math should not change anymore. And we still have as an objective to minimize the weighted compliance. So what we get in this step is basically a higher stiffness while obtaining the same mass. Okay. Last step we added to this process is topology. We call it topology optimization. You all know this from the metal optimization. If you use aluminum or titanium or steel, you can work with HyperWorks to get a topology optimization. We do the same with our monocoque, but with carbon fiber. So we just run the topology optimization in HyperWorks, and then you get these really nice small lines, which basically connect areas of high stress. And then after you see where you have areas of high stress and load passes, we put UG stripes exactly along these lines and obtain an even higher stiffness of the monocoque, especially for the torsional load case. After that, we obtain a plywood, which is basically we have, you can see here is the lower half of our monocoque, and where it's colored blue, we need to lay carbon fiber. We do different views for every layer. We export them to FiberSim. By now, there's also this function in HyperWorks itself, where you basically can export it into a DXF file or something similar. And then we load this into a software for our laser projection, and the laser projection is mounted at the top of our manufacturing hall, and then you project these little circuits onto the mold directly, and then you know exactly where you have to place your carbon fiber patch, which is really important to obtain a nice monocoque, because if you simulate all of it and then later on you put your patches a bit more to the left or a bit more to the right, or it's not the same direction, your simulation and your monocoque will be two different parts, and that's something you don't want. Yeah, that's all from me. Are there any questions?
So thank you, Robert, for this very interesting presentation. So it's really cool to see what you are doing, and also the level of expertise you have built up in simulation. That's really impressive to see also for me. So we had a few questions in the question tab. So one was, how do you model your core material? For example, aluminum honeycomb. So Julian Richter was asking that question. Can you answer that?
Yes. We just set up a core material like you do with foam, and then we do testing with the core, physical testing, and then we fine tune the material properties of the core.
Okay. So the core is modeled as one ply. So you model the core as one ply, or do you model it as solid material?
No, we model it as one ply.
One ply, okay. With the specific material data then in that ply.
Yes.
All right, okay. So Carmen Shishkov is asking, have you guys considered any fiber types other than carbon fiber to use in a monocoque?
We have played around with aramid to use. We also did some experiments with glass fiber. But when you use prepreg carbon fiber, it's not recommended to use aramid because of the different heat expansion rates. Not a good idea to do. We run into problems, and with glass fibers, we just found out they don't provide the material properties we need.
So there's not enough stiffness in glass fiber, or?
Yes.
Okay.
Not enough stiffness and too much weight.
Too much weight. I see. Okay. The next question is, how do you constrain your monocoque model to apply the kinematic loads?
Well, basically, we model the suspension rods as 1D tubes, and then we apply the loads. The connections we model as rigid, and after the simulation, we obviously look at some strain criterions as time or maximum strain criterion to see if everything breaks.
Okay, so you use the tubes for the chassis, and
yeah,
then
for all the wishbones or like push rods, or if you have a pull rod, we use just 1D tube elements, and the consoles we model in 3D volume elements.
Okay, and at the end of the rods, you just apply regular SPC constraints, like just normal single point constraints. Okay. So I hope that answers this question. Next one is, am I correct that you use a two-part monocoque? And do you have tips for placing your carbon layers when you produce a single-piece monocoque?
We use a two-piece mold. Yes, that's correct. Because we are not able to place our all of our patches the correct way if we would do it in one piece. If you do it in one piece, I highly recommend that you have huge openings. For electric cars, this is a bit difficult because obviously you will lose a lot of stiffness if you put a huge opening in it. If you use a combustion car with a metal rear frame, you can do it. But for electric cars, I don't think there's a way to do it, except you have a really wide car and you can properly stand in it. Yeah.
Okay, so you have one monocoque but two mold, so your mold is divided.
We split the monocoque in half, and then after that we join it with a lap joint. But the lap joint is really easy to lay because it's basically just one large stripe across the middle of the monocoque, and you don't have to layer complex shapes like some engines for suspension mounts, or if you have finicky engines for engine housings or something like that, then you really have to be careful to not get any tension into your carbon fiber. But if you just have a straight plane where you can lay carbon fiber, you can do it in one piece. And that's how we do our lap joint. We make sure that the area where we have to put the lap joint later on is as straight as possible and really easy to lay, because you don't have much space where you can lay in, and it's really dark inside there. So, yeah.
Okay. All right. So next question. I guess we have time for one or two more. How do you respect the SES layers in the simulation, or are you determining the SES layers right within the simulation?
For SES, we recommend that you finish your SES before you start simulating your monocoque. So you know what layers you need for your SES at least. And we incorporate them latest after the free-size simulation. After free-size, we have a look what HyperWorks recommends as layers, and when we do the cleanup, we set some layers as you can set them so they don't change anymore, and there we make sure that the SES layers are in there. And then we continue with the simulation, and after the simulation is finished, we redo all the SES testing, and by now this has worked.
Okay, and one final question: what's your target torsional stiffness? So how high is your target?
Target torsional stiffness should be so you achieve a linear behavior between front and rear axle. For us, it's around 3,000 Newton meters, but the torsional stiffness of our monocoques is way higher due to different load cases and the SES.
Okay. So thanks again for this very interesting presentation, and questions show that people are curious and enjoyed it. So thanks a lot. And yeah, I hope you'll also enjoy the rest of the day, where you'll learn a bit more about how to set up these models, how to set up these optimizations in the workshop that will follow later.
Yes, thank you, Jan, for the invitation, and have a great day.
Yeah, you too.